magnet can lift 1,000 times its own weight, yet it's made from rock pulled straight out of the ground. It never touches what it moves, but it can rip a wrench out of your hand from 3 feet away. Heat it past a certain point, and it forgets everything it ever knew how to do, permanently. That shouldn't be possible from a chunk of metal ore. So how do factories turn raw metal ore into a magnet precise enough to spin a hard drive, hold a smile on your fridge, and power an electric motor? Every single time, at massive scale. Let's step inside and find out. Most people think a magnet is just magnetic metal. It's not. Every piece of iron on Earth is technically capable of being magnetic, but left alone, the atoms inside it point in every direction at once, canceling each other out completely. A magnet only exists because someone forced billions of those atoms to agree, to point the exact same way, all at once, and stay that way forever. Everything that happens in a magnet factory from start to finish is really just an elaborate process of forcing agreement onto something that would rather stay chaotic. It starts with ore, usually iron, mixed with other elements depending on the strength required. For the weaker, everyday magnets you'd find holding a photo to a fridge, the mix might include ferrite, made from iron oxide and either barium or strontium carbonate. But for the strongest permanent magnets on Earth, the kind used in electric motors, wind turbines, and hard drives, the key ingredient is neodymium, a rare earth metal that isn't actually all that rare in the ground, but is notoriously difficult and expensive to refine into a usable pure form. That refining process alone can take weeks. The ore is crushed, dissolved in acid, and chemically separated from more than a dozen other elements it's naturally bonded to. What comes out is a fine, grayish neodymium oxide, a material that shows no sign of the pulling force it's about to develop. The raw material arrives at the magnet factory in dull, unglamorous chunks and powders. Nothing about it looks capable of holding your grocery list to a fridge, let alone lifting a car off the ground. The first real transformation happens in a furnace. Iron, neodymium, and boron are melted together at temperatures well over 1,000 degrees Celsius, forming a single alloy. This is a delicate balancing act. The ratio of these 3 elements has to be almost exactly right, because even a small deviation changes how strongly the finished magnet will hold its charge. Too much iron and the alloy loses magnetic strength. Too little boron and the crystal structure that gives the magnet its power never forms properly in the first place. As the molten alloy cools, it doesn't set into a solid bar the way you might expect. Instead, it's deliberately shattered, first into rough chunks, then pulverized into a coarse powder. This seems almost destructive, breaking apart something that took so much energy to create, but it's actually the most important decision in the entire process. Smaller pieces mean more control over what happens next. And what happens next is where the real magic, or rather, the real physics, takes place. That powder gets ground down even further, using specialized milling equipment, into particles smaller than a single grain of flour. Some of these particles measure just a few microns across, invisible to the naked eye. At this microscopic size, each particle is small enough to contain only a single magnetic domain, meaning every atom inside that one tiny particle is naturally inclined to point the same direction as its neighbors. This is the physical trick that makes the entire process possible. You can't force an entire solid block of atoms to align all at once, but you can force millions of these tiny single-domain particles to align one at a time in unison. Once the powder is fine enough, it's loaded into a mold and pressed inside an intensely powerful magnetic field, often tens of thousands of times stronger than Earth's own magnetic field. This is the single most critical step in the entire process. The external field physically forces every microscopic particle to rotate in place, twisting until each one points in exactly the same direction before the material is compacted and allowed to become solid. Get this step wrong, even slightly, and the finished magnet will come out permanently weak, no matter how well every other step is executed. There's no fixing a misalignment after the fact. It has to be right in that one moment, or the batch is essentially ruined. While still aligned inside that magnetic field, the powder is compacted under enormous mechanical pressure, sometimes exceeding 100 megapascals, squeezing the particles together into a dense, solid shape. From here, the piece moves into a furnace again for a process called sintering. Instead of fully melting the material, it's heated to just below its melting point and held there. The particles fuse together at a molecular level, becoming one dense, unified block, all without disturbing the microscopic alignment that was locked in during pressing. Skip sintering, or rush it, and the block stays fragile and porous, prone to crumbling under the exact kind of mechanical stress it's designed to withstand. After sintering, the raw block is still just a rough gray shape, not yet a usable finished product. It's cut using diamond-tip saws or wire cutting machines into precise dimensions. Whether that's a small disc for a speaker, a curved segment for an electric motor, or a thin rectangle for a fridge magnet. Every cut has to be exact because the shape of a magnet directly affects the direction and strength of its field. The bare metal at this stage is chemically reactive and prone to corrosion, so nearly every finished magnet gets a protective coating, usually a thin layer of nickel, sometimes paired with copper or zinc underneath for extra protection. This coating is applied through an electroplating process, where the magnet is submerged in a chemical bath and an electric current draws a microscopically thin layer of metal onto its surface. Without this step, a raw neodymium magnet left exposed to humid air would begin rusting and flaking apart within weeks, losing strength as it degrades. Here's the part that should sound impossible. The magnetic alignment step, the moment where billions of individual particles are forced to agree on a single direction, happens in a fraction of a second, on particles too small to see individually with the naked eye. And it's completely irreversible in one very specific way. Heat a finished neodymium magnet past its Curie temperature, often somewhere around 300 to 400 degrees Celsius, depending on the exact alloy, and that carefully forced alignment collapses. The atoms scatter back into random orientation, and the magnet loses its strength permanently, even after it cools back down to room temperature. All that precision, all that pressure and heat and chemistry can be undone by a single mistake at the wrong moment. Neodymium magnets aren't the only kind produced this way. Alnico magnets, made from aluminum, nickel, and cobalt, are cast rather than pressed from powder, poured molten into molds, and cooled slowly inside a magnetic field so their internal structure aligns as it solidifies. Samarium cobalt magnets follow a process closer to the neodymium method, but tolerate much higher temperatures before losing their strength, which is why they end up in aerospace components instead of household items. Ferrite magnets, the cheapest and most common type, use a similar powder and press method, but skip the expensive rare earth chemistry entirely, which is why they end up as the black, brittle magnets stuck to a whiteboard rather than inside a jet engine. The demand for these materials is staggering once you consider where magnets actually end up. A single modern wind turbine can contain over a ton of neodymium magnets inside its generator, wound through miles of copper coil. An electric vehicle motor typically needs several pounds of them. Smartphones use dozens of tiny magnets for speakers, vibration motors, and camera stabilization. Components small enough to be invisible, yet each one went through this exact same furnace to alignment to sintering chain before it ever reached an assembly line. Multiply that by the billions of devices manufactured every year, and a process that looks almost artisanal in its precision suddenly has to happen at an industrial scale every single day without a single misaligned batch slipping through. Before any finished magnet leaves the factory, it goes through testing. Machines measure its pull force, its surface field strength, and its resistance to demagnetization under stress, comparing every single unit against strict tolerances. A magnet destined for a hard drive has to meet far tighter specifications than one destined for a refrigerator door, because even a slight inconsistency in field strength can throw off the precision components it's paired with. Handling a finished magnet also comes with its own quiet danger. A neodymium magnet the size of a coin can snap together with bruising speed, trapping skin, or shattering if two full-strength pieces collide directly. Factory workers handle the strongest units with spacers and strict procedures, treating something the size of a bottle cap with the same caution you'd give a loaded spring. An object with no moving parts that can still injure someone simply by existing near another magnet. What started as dull, unremarkable ore, dug out of the ground and looking like nothing more than gray rock, is now a finished magnet, polished, coated, and magnetized with such precision that engineers can predict its pulling force down to a fraction of a newton before it's ever installed in a motor, a speaker, or a sensor. From furnace to powder to alignment to sintering to coating, it's one uninterrupted chain of forced order applied to something that would much rather stay chaotic. That's how a magnet goes from raw ore to something that can spin an electric motor, focus the sound in your headphones, or hold your kid's drawing to the fridge. Billions of atoms forced into permanent agreement on purpose under conditions most of us will never see. What sits quietly on your fridge door went through a furnace hot enough to melt steel and a magnetic field thousands of times stronger than the Earth's, just to hold up a grocery list. Precision most of us never think twice about, until now.